after the lunch, we are going to start. Okay. So this is session 3.
Okay.
Okay.
Should I start now or we should wait some time?
I think if you are ready, so we can start now. I am just posting in the group, so other participant then immediately they can join. Okay.
Okay.
Okay. Within 2 minutes, we will start. I am just posting in the group.
Okay.
Okay. Okay. Okay. Okay. Yes, your slide is visible. Yes.
Yes, sir. Yes.
Yes, it is full screen now. Okay.
Okay. Should I start, sir?
I'm requesting the participant, please mute yourself. Please mute yourself. Otherwise, it is very disturbing to the delivering person. Okay, Manush, we can start.
पैसे जमा कर दिए ऑनलाइन, आप हो जाएगा एडमिशन आपका, कहाँ फॉर्म दीजिए, ऑनलाइन कर दीजिए.
Hello everyone.
हाँ, मैं आपको अकाउंट नंबर दे रहा हूँ, उसमें पैसा ट्रांसफर कर दीजिए, आपका रसीद मिल जाएगा, एडमिशन डन हो जाएगा.
Manush, please unmute yourself. I have muting all of them actually. Hello, Manush, am I audible?
Yes, sir.
Actually, I'm muting all of them. That's it.
Yes. Okay. Am I audible now, sir? Hello.
Yes, you are audible. Okay. We'll start.
So hello everyone. Myself Ranjan Jena. I am working as a senior power electronics engineer in L&T Technological Service. So today I am going to take this workshop session, which is efficient torque control of IPMSM using efficient. So I will take efficient torque control of IPMSM using MTPA algorithm on C2000 DSP platform with embedded MATLAB coder. So these are the outlines. So before I am going to start, I am going to give you a brief introduction about this IPMSM drives and the self-correction method we have developed for MTPA control algorithm, and after that we are going to present means the implementation of this algorithm with the vector control and with C2000 microcontroller. So we are going to discuss everything about how to implement this, how to how to design the experimental prototypes. After that, we are going to conclude this session. So here you can already know the importance of machine drives in the modern days. So it means the drives are actually the modern drives are actually to enhance the efficiency, productivity in the various industry, and which makes them the indispensable parts of this modern technological landscape. So here you can see that there are 3 IPMSM drives which are generally used for EV, and you can see those EV motors are integrated into power electronics devices, which has to integrate in one one compact size to reduce the volume, and for that we can significantly reduce the space and volume of such kind of drives, and also it helps to reduce the cost, to reduce the environmental impact, and also to maximize the performance of such kind of drives. So generally in this kind of machine drives, this power control architecture are generally employed. So where we are getting DC voltage from either energy storage device, which are generally here lithium ion battery, and from that actually there are different components are there. One is auxiliary DC-DC converter to power low power converters or DC-DC converter, and also we have the solid state inverter here. Means generally these are two-level inverter for low power application. Means I am telling low power means below it is 50 kilowatt. So above 50 kilowatt, generally three levels or multi-level inverters are used. But some exceptional case means if you consider Tesla and other kind of EV, they are going for 500 kilowatt with two-level inverter also. So that is basically depends upon the what kind of cooling mechanism they are using. So we are not going to look into that inverter part. So here you can see that these inverters are actually supplied three-phase power to these electric machines, and from electric machine we are taking some measurements like voltage, current measurements, torque, not torque, means basically rotor angle, speed measurements, and also there are temperature sensor are also there to give real-time thermal data to the controller. So here you can see that this is the conventional control algorithm that are implemented in this kind of drive, where a controller will calculate the optimal reference current, and according to those currents value, there are two current loops are there which will calculate the required voltage for this electric machine, and using digital control switches, means power turning switches, we are applying switching voltage to this electric machine to maximize the efficiency. So this in this optimal state computation, there are many algorithms are there which considers different state variable, and which will maximize the means normally this is for only to maximize the efficiency. And so here in this kind of drives which you see in this figure 1.1, these are the percentage of equipments, means components are used. So generally energy and for that the cost are associated also with this kind of components. So you can see energy storage devices are taking the large part of the cost, which are now it is lithium ion. You already know, means we are also going for sodium ion and other substitute, but till now we are not able to get that much energy density from, means compared to lithium ion. And if you see, the IPMSM is also taking huge part of the total cost of the systems, and power tonics you will see means these are becoming cheaper. So now sensor controller, these are all becoming cheaper because of increasing number of electric vehicles in the market, and that's why production is increased. But in this IPMSM monopolies are there, means we are using permanent magnets which are which we are importing, means everyone's are importing from China, and energy storage devices which are lithium based, and we are unable to get lithium from, unable to produce. So these are all factors which are affecting the total cost of this kind of drives. So as you can see, the machine drive technology, there are various factors are there to choose which kind of motor we should go for, and also we should have means different criteria for that also. So there are, you can see means we have to reduce the energy conversion, means we have to improve the control precision. Also the cost should be minimum, means operational cost should be minimum, and also it can be integrated to smart technology which are IoT and different kind of technology which are now being used in mm, uh, modern industry. So also you can see there are three motors are already available in the market, which is induction motor, surface provided magnet, synchronous motor, IPMSM. And then generally why we are choosing IPMSM is that it is giving higher efficiency compared to other motors. So this efficiency diagram is taken for a specific motor part, so we cannot guarantee that this is valued for all motor at other specific mm, means other specific power. So here it is generally this induction machine is actually aluminum case. So we have a different efficiency plot for copper case also. So in that case, we are actually getting comparatively same efficiency plot compared to IPMSM. So okay. So this one is not in our analysis part. Okay. So here you can see that the permanent magnets are used in this kind of EV train motor. So in there, you can see the flux density means because we are using means variable flux here, means we go for field weakening method. So that's why the area of this flux density is comparatively higher than with other motor. So generally you can see the construction of this IPMSM, so which is actually interior permanent magnet synchronous motor. You see in this figure, see how those magnets are placed inside this rotor structure. So starter structure are all same, having I think 24 slots, and those permanent magnets which is actually showing here mm, mm, means those permanent magnets are glued on the surface of the rotor. So that's why it is not able to rotate at higher speed because of the centrifugal force. It will break down. So that's why means we try to put those magnets inside the rotor. So here in this figure 1.6 C, you see those magnets are placed inside the rotor. So by placing this magnets inside this rotor, we are able to increase the reluctance torque as well as the means reluctance torque, and also so that is the benefit we are getting here. So you can see the permanent magnets volumes are also reduced. So by using IPMSM, we can reduce the dependency on the import of this permanent magnet. As you see, means then we try to reduce permanent magnet more. So that's why we go for means one layer. It is in the C, it is one layer. Here we go for two layers. So basically we are trying to increase the reluctance torque. So in that case we are trying to reduce the permanent magnet volume in the rotor, so that we can reduce the cost. So from that we go for IPMSM to permanent magnet synchronous reluctance motor also. So where there is no need of permanent magnet here, and using the reluctance of the torque, we are able to generate torque for machine drive. So here we are not going for synchronous reluctance motor. We are just going for this IPM interior permanent magnet motor, so which are generally adopted by all EV manufacturing company because of its high power density, high speed characteristic. And so we are switching to synchronous reluctance motor. reluctance motor also, but those are limited to only for constant speed application and not for high power application because of a noise issue. So there are many issues are there in synchronous reluctance motor, but in future we'll see them also in electric vehicle. So for interior permanent magnet synchronous motor, you can see the torque load torque characteristic, as you can see from figure 1.7, the load torque characteristic and the MTPA trajectory we are here choosing to maximize the efficiency. So maximize efficiency means we are trying to increase the load means by reducing the current, so that means by minimizing the current. So we are trying to minimize the current as much as possible for a specific load torque. So from that we are able to reduce the copper losses and also switching losses, which is means if we reduce the current in the machines, it will eventually reduce the current in the inverter, and also use the inverter. If there is decrease in the current in the inverter, automatically conduction loss and switching loss will also reduce. So by implementing this MTPA algorithm, we are trying to reduce the losses, means mainly copper losses. So that's why we are going to present here. So based on that, we require means optimal current reference generation here. So these current reference are generated from this MTPA algorithm, which are being used by two current control loops, so that we can regulate the required amount of voltage required for our motors. So means from the first we have our assumption that the motor parameter are constant. So based on that motor parameter, we are actually calculating this DQ axis current. So but as you can see from this figure 1.6, there is a variation of the motor parameter according to the operating condition. So at a high means there are chances that when temperature will increase, automatically the starter resistance will increase, and also due to the saturation on the DQ axis, means D in the D you can see means D is aligned with the permanent magnet axis, so the reluctance is always high. But in the Q axis you see means you will see only the iron path, so it easily saturate in high current. So there is a reduction in the Q axis inductance at a high current. So that and also D axis inductance is also high, but their percentage of variation is limited. So because of that variation, we are not able to accurately implement this MTPA trajectory. So we require different kind of estimation techniques, so which will estimate these variables, means D axis inductance, Q axis inductance, flux linkage, and you see here the flux linkage is estimated from the temperatures, because automatically if you see the permanent magnet characteristic, you'll see with the variation of the temperature, the permanent magnet flux will decrease, or due to the demagnetizing current. So here one method is developed to directly estimate this flux linkage with the temperature, and also this DQ axis inductance are also. Hello? Anybody is saying anything? Hello? Okay. So here, am I audible? Hello?
Yes, sir. Audible, sir.
Yeah.
Yes, sir, you are audible.
Okay.
Please continue.
Yeah. Okay. So here you see this D axis inductance, Q axis inductance are dependent on their corresponding D and Q axis current. So according to the experimentation, we are able to estimate those parameters at different operating points. So that is how we are able to estimate those parameters in offline, and by using lookup table, we implement those D and Q axis inductance so that there will be no deviation in this MTPA trajectory. So, but these requires offline estimation, which consumes a lot of time before, say during experimentation at different operating point. And if you have multiple motors, then you have to conduct this kind of experiment for all motors. So also there is also a problem with manufacturing. So where you are trying to produce the same motor, but the parameter will automatically vary. So there are many factors are there. So because of that, we are not actually adopting this kind of algorithm which required large offline experimentation. And for all offline experimentation, you require additional torque transducer and also dedicated hardware, dedicated. Um, so for that, will be very much time consuming. So you have to install those permanent, those motor with your with your is that called that your load motor means. So those are very much time consuming. So that's why when you are proposing other kind of algorithm where we are trying to perturb the input point. So you can see this current curve here. So here this is the minimum current point. So we are trying to achieve this for a specific load. We are trying to achieve this minimum current point. So by perturbing certain state variable, we are trying to change by changing this means if I will inject a small oscillation in this current angle, I can check that whether current is increasing or decreasing. So if I will get those information, so by optimal computation, I can find this beta m. So from that I can get optimal current value. So from that IS, I will easily get this DQ axis current. So these are all part of complex algorithm which requires a lot of computational resource, and also complexity is also high. That's why it generally these are restricted only for academic. Okay. So our requirement for this kind of drives is that it should be simple, it should be reliable, and also where we can get maximum efficiency as much as possible. So, and also it should be compatible with emerging technology, so we can integrate it with other possible things if it is possible. And also we need to minimize those cost also. So that is the important criteria for any kind of machine drives which are being implemented in all kind of industry application. So these are the requirements. Mainly these are motivation we have in mind when we are trying to develop something. So here we are going for design and development of this MTPA based IPMSM drive, and so from the starting I will discuss about the modeling implementation of vector control of IPMSM with MTPA. Then after that design FTI lab, which is based on C2000 microcontroller TMS320F28379D, and how I integrated that microcontroller board with IPMSM prototype, and after that we are going for evaluation whether we achieved our objective or not. So these are some points I'll just you can look at it. So before that, I will go for this mathematical modeling of IPMSM. So generally, this is the three-phase equation for this IPMSM, because we have already permanent magnet, so we have a permanent magnet flux linkage. So according to this three-phase theory, you can see the value of self-inductance, mutual inductance, which is a function of rotor angle, and also the flux linkage in terms of permanent magnet flux linkage, and also with magnetizing inductance and leakage inductance. So here you can see these three-phase equations are dependent on the means these are all means time means associated with the time variable, because this theta r is equal to your omega et. So omega e is your angular speed in electrical radian per second. So these are all time dependent. These equations are all time dependent. So it is very difficult to go for a analysis using this three-phase equation. So what we go for this kind of equation is that we go for transformation. So these are simple transformation. You already know these kind of transformation in your study. So we are here using Clark and Park transformation. So here we have used a simple Clark transformation. So from three-phase equation, we are able to change it to two equation. But still, you see this in this means we have changed the ABC to alpha beta. So alpha beta. So that is also synchronously. This is your stationary reference frame. So your alpha beta is a stationary reference frame. You can see from this equation. This equation is still dependent on the time variable, that is theta r. So that's why it is also difficult to implement any kind of algorithm means with in alpha beta stationary reference frame. So we go for this DQ reference frame, in which this DQ reference frame is rotating with the rotor. Means in that case, the relative motion between the rotor and this DQ axis is 0. So from that, it is called synchronously rotating reference frame. If we have a difference in the angular speed between this and this, we have the sinusoidal means part automatically come into picture in this equation. So we are trying to get this theta r. So that is the angle between this alpha axis. Alpha axis is your a axis. So by getting this theta r accurately, that is the prime derivative. Means that's why we require means absolute encoder. Means for IPMSM, not like induction motor. In induction motor, we require the relative encoder or incremental encoder, which do not have a Z part. Means what is that called? ABZ. There are three parts we will get from the encoder. So if basically with AB we will get relative position, but with ABZ we can get absolute position. So that's why. So by using the theta, means the absolute value of the rotor angle, we are able to get this voltage equation in DQ reference frame. Here you can see that these equations are not do not have any variable that is dependent on time. So these equations are time independent. So we are able to get this DQ axis voltage. You see, means this is the required amount of voltage required for motor at a specific current value. So the other are the just parameters, and this is the equation. Means in the transient state we have also means di. That's why we have di ds by dt, dqs by dt, and these are cross coupling parts here. Means there are means you see these id have a IQS part and QXS voltage at DS part, and also the permanent magnet flux linkage. Means here we can say it is the back EMF here, which is reflecting on the q-axis voltage. So here also we have this zero sequence equation also, which is associated with this zero equation, zero axis current and also leakage current. So basically in the motors what we have only 3 terminals, not 4, because we are not accessing that neutral terminal of that motor. Generally we are not using that neutral part, so that's why it is balanced. So for balanced system we do not require this zero sequence, so we are not going to use in further analysis. And there are multiple drives are also coming which are using this zero sequence part also for voltage boosting, charging. So in that case the analysis will be different. So let's go to the next. So here you can see that using this two equation we have two circuits here. You see those components, dq axis voltage parameters and those cross coupling terms. So as you can see from the this is just a Kirchhoff's law. That means you can get easily from this figure, means which equation, and with means this is your normal formula to calculate the input power to the motor, and from this input power you can see that means the first part is the loss. This is your copper loss 3/2 RS IT square IQ square, and other is the energy store, means how much energy is stored in this IPMSM from means when you switch. Means and after that another part is your how much energy is converted from the electrical to mechanical part. So the useful thing we need is this mechanical part, means how much electrical energy is converted to mechanical energy. So from this we will solve this. We will get this equation here: lambda m IQ plus LD minus LQ ID IQ. So here you can say there are two parts in this torque equation. One is the permanent magnet part, means which is associated means with this flux linkage and IQ, and LD minus LQ. So this is the reluctance, means if you are able to increase the difference between this LD minus LQ, so we are able to increase the means we are able to produce the torque. So if this lambda is missing here, so in that case also we can generate torque with this kind of PMSM, sorry, IPMSM. So that is actually going for the synchronous reluctance motor where the permanent magnets are missing there. So there is no lambda in there. So from that the equation will be only T is equal to LD minus LQ ID IQ. And here you can see that because of high reluctance on the T axis path, the T axis inductance is generally lower for IPMSM. So in order to produce positive torque, we need to give either this ID or IQ is negative. So generally IQ is directly related to T. So with positive current we will get positive torque. So we have to inject a negative current, negative direct axis current. So with the negative direct axis current we are able to generate positive torque. But with the negative ID, means it has a demagnetizing nature. So it will forcefully try to demagnetize those magnets which are generally buried inside the inside the rotor. So generally in SPMSM where those permanent magnets are glued on the rotor surface. So there you cannot see the difference between this LD and LQ. So there means the reluctance torque is missing in surface permanent magnet synchronous motor. That's why the power handling capability of such motors are lower. That's why we are not able to get high power in SPMSM. So for high power expression, we have to go for this IPMSM where the permanent magnet torque and the reluctance torques are distributed. And also you can see this means from this two figure we are able to make a graphical representation where this is your cross coupling here, means one flux q-axis flux is affecting this d-axis voltage and d-axis flux is affecting this q-axis voltage. So these equations are generally non-linear, so we have to linearize it before implementing any control algorithm. And also you can see these are parameter dependent also. So in order to linearize this, we need complete information. This means accurate information about this LD and LQ, and also starter resistance, and also this lambda. So there are many methods are there to estimate, means preliminary estimations. Many methods are there to calculate this value, but those are also ambiguous, means those are also will vary into a operating point, but we'll see those things later. So these are the, in the figure 2.5, you can see that this is the conventional algorithm, in the field vector control algorithm, which are implemented in the PMSM. So the same thing is applied for IPMSM also, where a inverter, a three-phase inverter will supply three-phase power to your IPMSM, and also the rotor angle is means which from a incremental encoder or a resolver, means so in the resolver you have variable reluctance resolver, wound resolver. So those are all absolute kind. So because of this absolute encoder, the cost of these kind of drives are dramatically increased, and that's why you are not actually seeing this kind of drives in EV, means in two-wheeler. So generally those are all BLDC motors. So, and also there are also other requirement, means it requires at least two current sensor, voltage sensor. So, and also you see the complexities are also high comparative to BLDC drives. So with this equation, by putting this cross coupling part to the right side, means with estimated value using LDLQ. So these are all estimated. You can see from this figure 2.6. So we are adding this decoupling term to remove this cross coupling in this control loop. So this is the part of the IPMSM, and this is the current loop. So here we are getting this ID and IQ by using those transformation formula. So so from three-phase current sensor, so three current sensor, we are getting those IB, IC three-phase current. Then after clock transformation, we change to stationary reference variable IL phi beta, and using clock transformation, we got this DQ axis current. So from this DQ axis current, we have implemented a simple current control loops, and using PI regulator and these values, this decoupling value, means which are based on estimated LQ star and flux linkage and D-axis inductance. We first decouple this algorithm so that the equation will be linearized between this ID and the applied voltage. So here the applied voltage will become UD plus WR LQ IQ. So WR here is the speed in electrical radian per second. So according to this formula, we are able to get our DQ axis voltage using just a PI control.
Sorry, yeah, sorry to disturb you, sir. Like, I think in between your voice is breaking. Like, there is some, like, I think your mic was
okay. So you are only getting the problem, or someone else? Hello.
Okay, but carry on, Manoj. But I'm clearly listening. I'm able to hear clearly.
Is it okay? Okay. Okay, you kindly check your network connectivity. I think you have problem from your side.
Okay.
Properly audible now.
Okay. Oh, okay. So here you see, means after this decoupling term and implementation of API controller, we are getting these two equation here. Means means where both the D and Q axis loops are linearized, and using PI controller we are able to regulate easily. So the main fundamental of MTPA is that how to get this ID star and IQ star. So that is that's what we are going to discuss here. So these are some control tuning parts. So means which are generally done for any kind of current loop. So here we are choosing pole zero cancellation method. So according to that, we means before that we have to choose the bandwidth. Generally, those bandwidths are restricted to 1/10 of the switching frequency. If you have 2 times sampling per switching period, and for 1/20, if you have 1 time sampled from carrier signal. So according to that, the performance of your current loop will be decided. So here it is chosen, means according to some experimentation, we have chosen it here 2000 radian per second. So here the switching frequency is 5 kilohertz. So based on that, we get our means PI controller variable KPD, KID, KPP, KIQ. So based on these are all based on the parameters. So you can easily get those by just test your motor and you get your this preliminary or means no load value, means LQ, LD. These are all taken from the no load parameter of the motor. So automatically when parameter will vary, these value means the parameter operating points are will means when parameters are changes, these values are also changed, but the performance is not that much affect the control loop performance. So based on that variable, you can estimate this open loop frequency response, closed loop frequency response. So it you see, means by this pole zero cancellation, means it will behave this your open loop gain will behave like a integrator. So from that you can see the means cutoff frequency here. So here is means according to the value of your PI controller, your cutoff frequency is here 2000 radian per second. So like that you will get your closed loop performance also, where your closed loop gain will be 1/√2 here, √3 dB, also 3 dB, minus 3 dB. So after tuning, you can verify your control loops by giving a step signal. So you can see the performance of your D and Q feedback, means D and Q axis current. So according to your bandwidth, your rise time will be decided. So the more bandwidth, the more faster your system will be. So, but you have a limit on your bandwidth selection. So therefore, your rise time also limited, means how fast your motor can respond is limited. So if you want to improve this performance, means if you have a constant on bandwidth, if you still want to improve the performance, so that you have to increase your switching frequency. So by increasing the switching frequency, you will increase your power loss. So according to that, you have to make a trade-off, means how much frequency. And if you have a high power application, for that you cannot increase your frequency there. But for low power application, means if your inverter can handle that much power, and if you require for position control, like means, precision control. So in that case, if you require high bandwidth, so in this way you can do that. And also there are other factors also. You cannot just increase your switching frequency. You have to go for your control algorithm also. So generally these are also taking times. These algorithm to execute means according to your microprocessor, means what you are using, at what frequency you are operating. So in that case, how much time your algorithm will take to execute, means to calculate this ID, IQ, VB, VC, means your SB, space vector modulation. So everything will take time to execute in your microcontroller. So based on that, your how much cycles it will require. Means if you increase the switching frequency, so automatically a delay will appear in your system. So that will also hinder this dynamic performance of such drives. So, but high power application you can choose means according to your power need, according to the inverter means your in according to your inverter power, or so there are a lot of things in that. So we're not going to discuss those also. So here you see means because of limited ceiling voltage, your applied voltage is also limited. So you cannot give a more voltage than this K VDC by √3. So this is your ceiling voltage here, and your K is not 1. It is lesser than 1. It is around 0.9 to 0.95, because there are dead time. You have to put dead time. Also there are switching voltage drop also there. Means, in the switches. So there are resistance, means your DC bus resistance, those AC where you are using all have a resistance. So you are not able to give the required amount of voltage what we want. So that is the voltage. That's why we have to put a voltage limiter here. And I think because of that voltage limiter, we have to implement a wind up. So when your voltage is already in the verge of saturation, and when you are trying to change the reference, in that case automatically the delay will appear. See, your control loop will not behave fast because your integrator is already saturated there, and to reduce that we have to implement a anti-wind up. So in that case, you means it will automatically reduce the integral gain in that loop. So if your voltage is saturated, so this is actually done at means at this means we should not violate this condition 2.36. So and if we violate also, this anti-wind up will also going to handle, but at the saturation you are not able to regulate your motor. So this is how this anti-wind up structure are implemented in the both the DQ axis. So you can see this is a also here, and so it is the complete structure of your current control loop, both current loop in one figure, and your decoupling part is here with estimated parameter, and also we are taking ceiling voltage from this inverter. We are sampling voltage. So with current also we need to sample this voltage, but if you are sure that the voltage will not vary, there will be always variation of the voltage, because if you have energy storage, then it will be very. If you have a strong energy storage, means it is connected to grid or somewhat where voltage is not fluctuating, so you can eliminate this voltage if you are so sure that. But if those capacitor, this link capacitor are not properly placed, so when you change the load condition, you will see there is a variation, or there will be a ripple in the voltage. So it is better to use a DC current, a DC link voltage sensor. And how you are going to sample this is also a case here. Means you do not need to sample at the same sampling rate with your DQ axis currents. So generally, it can be sampled at low sampling rate also. Okay. So this is the total design, and by end of these are the equations we are getting, means to calculate this UD D axis voltage and DQ axis voltage. So from this DQ axis voltage, we need to implement this space vector algorithm, a space vector pulse width modulation, in which we are actually getting more DC bus voltage, DC bus voltage utilization. So SPWM are also present the sinusoidal pulse width modulation. So those are simple to implement, but the voltage utilization is lower compared to space vector. So this is space vector, and generally these are complicated. Means if you go for sector calculation and other, these are complicated. But if you directly go for just for implementation where sector information, this dual time information are not required, so you can go for that min-max method. So with min-max method also we are getting the same voltage utilization, and both are same, means, but if you required, means current information at a specific peak and valley point, so in that case the information of this zero vector is required. So that's why we have gone for this sector calculation based, and you see there are trigonometric functions there for dual time calculation, and here your modulation index is defined as √3 US by VDC by √3. So the maximum voltage you will get is VDC by √3 here, but with SPWM it is VDC by 2. So there are 15% more voltage utilization. So the more voltage you are able to utilize from DC, the more speed you can get in linear region. It is not about, means we are not operating at high over modulation region. It is in between the linear modulation. Okay. So the TS is the switching period, which means these are some sector and active vectors according to that. Say general formula, you have to just put your sector number and you will get your dual time. So after that, we have to implement a speed control loop there, and the bandwidth of selection of this speed control loop is also depend on the current control loop bandwidth. So as you can see from this figure 2.15, the current controller is simplified to 1. This is done because your speed loop bandwidth is generally taken 1/10 of your inner current control loop. So if your bandwidth is your outer loop bandwidth is lower than your inner loop, so automatically the current controller will, the loop gain will become 1. So you can see there is no effect of this current control loop dynamics to your outer loop. So you can simplify this analysis by just considering the current controller gain is 1, and according to that we can make the same kind of analysis that we have done for current loop, and with the pole zero cancellation we are able to get those PI controller parameter. And here you can see that this is your closed loop equation here. So here it is also it is looking like a low pass filter here. Omega s is your cutoff frequency or maximum bandwidth. So omega s by s plus omega s. So this omega s is generally 1/10 of omega here. C, current control loop. So and with this also we have to implement, because your their voltage is limited. Current control loop voltage is limited, but here currents are also limited. So in the IPMSM, you cannot drive more, you cannot put more current automatically. The temperature will increase and it will burn your starter winding, and also it will burn your inverter also, what we have designed according to the temperature limit. So from that temperature, you cannot, because of limited temperature, sorry, current carrying capability, your torque is also limited. So generally, 2 times rated torques are allowed, means it is allowed for good dynamic performance. So means that is not means continuous torque, the intermittent torque. So because of this, we need to implement a torque limiter, and because of this torque limiter, we have to again implement the anti-wind up structure here also in the speed control loop. So this is the equation of your speed control loop based on this 2.53. So now we'll go for this current reference generator. So here you see, I've already discussed about there are 2 parts in the torque control loop, sorry, torque equation. So one is the torque which is generated by the interaction of permanent magnet flux linkage and Q axis current, and also the reluctance part, which is because of the saliency on the in the rotor. So because of the saliency, we have the variation in the LD and LQ. So with that, we are able to generate this reluctance torque. So after some analysis, as you can see from this 2.17 on 7 with the current angle beta, we can get this coordinate and abscissa here, is cos beta and is sin beta. So by putting those equations, we are able to get this optimal current angle, that is beta m, and means with this means at operating point, actually del T by del B is 0. By changing the current angle, there is no change in the torque. So if you make it 0, so we'll get this MTPA equation here. So, but this is in terms of correct angle beta m. So this you can see from this 2.58, it is based on the parameters. Means it has 3 parameters, that is the flux linkage, permanent magnet flux linkage, your D axis inductance, Q axis inductance, and with a variable here is your IS, that is your starter current. It is the peak of your starter current, not RMS here. So this will work only for your base speed, means below base speed operation, not above base speed. So above base speed, you cannot implement this MTPA algorithm, and you have to implement field weakening control algorithm at the time. So in that case, you cannot reduce means the current there. So current is will be maximum, and voltage is also maximum at there, because you are operating at above base speed. So in that case, we are trying to reduce by injecting more demagnetizing current. We are reducing the permanent magnet flux. So if you reduce, means if you put more demagnetizing current, so there is a chance that it will damage your magnet. It will completely demagnetize your magnet. So that is the problem actually many EV manufacturer facing. That's why they are not implemented this into wheeler. So you will see in that case, your permanent magnet need to be replaced. So some cases happened when those magnets are completely demagnetized. There you have to remove that one and replace it with new one. So that is because of this demagnetized current. So this is a algorithm to put this field weakening controller here. So that is based on the means this maximum voltage criteria, where because we are operating at the base speeds, means in that case we have to apply base voltage. So base voltage is what is the maximum voltage we are getting from the inverter. So with this K factor, we already reduce the voltage from 1 unit to 0.9 or 0.95. So there is already 0.5 or 0.1 reduction in the voltage. So because of this field weakening, we have to reduce it more. So to give a gap to control, means for field weakening control. So this algorithm will inject d-axis demagnetizing current into this d-axis control loop, and with that, because our maximum current is already limited, so we have, if you will put more demagnetizing current, so we have to reduce the quadrature axis current also, because our maximum current is constant. So that's why with field weakening control, we are able to get a more speed but less torque. So that's why it is called as a constant power control. So as you can see, there are 3 loops are there, 2 current loops, 1 outer speed loops. So we cannot say this is a voltage control loop. This is actually to regulate the speed here with the voltage. So there are 3 loops inside. So, and here this MTPA algorithm will calculate your optimal DQ axis current, which is now based on this parameter, this lambda m, LD, and LQ. And there is a PI controller which will regulate your speed. So based on the speed error, we are calculating this current requirement, and from this current requirement, we are going to means with this 2.58, we are going to calculate this current angle, and from current angle, we are going to calculate this DQ axis reference. Then after that, it will go for inner current loop, and inner current loop will calculate this Q quadrature axis voltage, D axis voltage. Then after that, it will go for a inverse path transformation. From that, we will get this stationary reference voltage, and with stationary reference voltage, you can easily convert it to ABC, means voltage in 3-phase voltage, and with 3-phase voltage with the inverter, with the PWM strategy, you are able to drive your motor. So here we have placed an encoder here to calculate your rotor angle. So these are the means conventional algorithm which are generally found in electric vehicle which have IPMSM. So now we'll go for this power loss analysis. So in the motor, actually we did not consider the core loss. So the core loss part is in parallel with your DQ axis applied voltage. So core loss is depend on not only on the current, it also depend on the speed. So if there is more speed, automatically your fundamental frequency will be higher, and automatically core loss will also become higher. So for low power motor, generally this core loss is very low. So we can remove this part in this analysis, and generally it is not considered. Means we are not able to regulate this core loss. So generally, to improve the efficiency, we can have only starter loss in our hand, and also if you want to further if you want to reduce further power loss, we can go for SIC based, means inverter design, where efficient switches need to be placed instead of these conventional IGBT MOSFET switches. So for this IPMSM, we will go for only for the copper losses, where these core losses are neglected. So these are only happening for low to medium power motors. So as you can see from this, equations are now modified with the variation of parameters. Here, see the UT and Q axis voltage are now with D and Q axis inductance, but those are also a function of ID and IQ. I have shown you in the previous slide that these are function of ID and IQ. So like that, we have written those equations, and based on this current angle, we have the relation between the starter current and DQ axis voltage. So this is the same torque equation, and you can see the rotor structure here. Means this is a 4-pole based V-type interior permanent magnet synchronous motor, and here you can see the T axis is aligned with your permanent magnet. So here two magnets are there, N, S, and S. So and using so this is the internal of a rotor of IPMSM that I have used in my PhD, and this is the variation of permanent magnet flux linkage with quadrature axis current. Why it is written in the quadrature axis current, not in the with IDU? Because it is very difficult to get this parameter. This is your flux linkage part, and it is actually should be a function of IS. But generally, when we are testing the motor, we generally take ID is equal to 0. So it is mentioned under H. Here the flux link means quadrature axis inductance with D and Q axis voltage. Sorry, D and Q axis current, and also diode axis inductance in terms of D and Q axis current are also shown. You can see that there is a large variation in the quadrature axis inductance, but not with the diode axis inductance. This is because we have high reluctance on the D axis path, because there are two magnets are there, and as you know, permanent magnets have same permeability with air. It is same permeability. So you can say there are obstacles here, but in the Q axis, if you will go from the Q axis, there is only iron. Means it is not obstructed by any air gap, except those air gaps. Means between your starter rotor, there is no obstruction, because this hollow part will be covered by your axle. Okay. So that is also iron. Okay, but these slots are will be filled by magnets, and it has same permeability with air. So if you have magnets or not, that is not matter. Means LD and LQ will have same variation with your D and Q axis current. So here you can see the variation of MTPA trajectory due to the variation of this quadrature and direct axis inductance. So because of that, if you plot your MTPA trajectory, means according to the formula, you will get this blue line. But our actual MTPA trajectory is where you are getting maximum torque at minimum current. So you can say where this load torque is actually interacting with your real MTPA. That is your MTPA point at rated load. Okay, so here you can see the current value is lower compared to that means the MTPA. So here IS2 is lower than IS1. So at real MTPA, we are able to increase the efficiency. So we were able to reduce the losses. Okay. So as you see at figure 2.23, this is the same control loop that I have discussed, but I have removed that field weakening part. So here, instead of putting those PI controller, I have just combine them with speed regulator plus MTPA. So if you want to put MTPA, then you need to calculate ID and IQ separately. If you do not want to put MTPA, so in that case, you just simply put ID reference at 0. So that is actually happened in surface permanent magnet synchronous motor, where ID is generally taken 0, because we are not able to generate any reluctance torque, because there is no saliency there. Okay. So our objective is here is to minimize this starter current subject to this load torque, and with you can see that there are two equations are there. From that we are getting the same conventional MTPA equation in terms of current angle, that is also based on these parameters. So these are generally employed in all kind of machine drives which used MTPA, means without any additional control structure. Okay, this is the most basic version of that. Okay, so as you can see that because of the parameter variation in the motor, we are not able to get means minimum current at del T by del V 0. So this is the criteria we are actually calculating the optimal current angle, but due to the parameter variation, we are not able to get our minimum current at that calculated point. Okay, we are getting this del T by del V, we are taking beta, but here you can see that IS1 is higher than IS2. So that's why what others are doing is that they are implementing LUTs. As you can see, figure 2.6, there are two LUTs are there, which is depend on the torque and also on the speed. So these are all are taken from a specific motors by they have gone through multiple testing, multiple experimental procedures. Then after that, they got this current LUTs, and based on the operating point, they are putting those ID and IQ value for the current controller. So in that case, they can get maximum efficiency, but these implementation are taking, it generally takes a lot of time, and for that infrastructure are needed, times are also required. So that's why we go for estimation method. So is there any other way to go for MTPA method other than this, this conventional constant parameter based and LUT based? So that's what we try to implement. So as you can see from this equation, there are three parameters are there in this conventional MTPA equation. So if you can write this in terms of base current, so here this IB is a base current. I am telling this base current is that in the torque normalization method, we are generally try to remove this dependent on this dependence on this parameter. So we called it as a base current so that we can calculate the base torque. So base torque is not your rated torque, or this base current is not your rated current. Okay, we just assume this as a base current. Okay, so based on this value, we can easily get our per unit D and Q axis current. Okay, so here we can modify that equation, that same equation we have modified with this base current value, and there are two variables are there, only IB and IS, where IS we are regulating and IB is either constant if parameters are not varying, or it will vary if those parameters is this, the three parameters are varying. Okay, so So this IB, if you are able to regulate this IB, we can easily get this V time. So that is the work I am going to present. So by simplifying this equation, you can see that, and also you see this square root term, this cos inverse. So those are means computationally not efficient to calculate in a microprocessor. This will take a lot of clock cycle. Okay, so and it will consume more. That's why we are not able to reduce the computational time of a algorithm. So we're trying to avoid this square root term and also this trigonometric term. So after some mathematical derivation, we are able to get 3 equations. So here you can see that by so in that case we have to implement. You have to introduce another control variable here. So that is called IN here. So before we choose this IS as a control variable to calculate this DN QXS current, but here we are using this new variable which is IN. So you can see that the variation of IN with the torque is the means it looks linearized, means there is a slight curve here, but it looks linearized here. So by introducing, there is no problem with this introduction of this new variable. So means with less variation in the IN with method 1, there is means there is tremendous increase in the torque here. You can see that, but with others it is not. So with this 3 method, we are able to regulate our torque with our new variable. And also you can see that with the different methods, how we are actually getting this MTPA trajectory. So here, so this is our original one, actual MTPA trajectory. But with this Taylor series of expansion in the method 3, we have a little deviation here. But it is very easy to implement. You can see that IN is equal to IQ and ID star is equal to just minus IN square by IB. Minus is there because we need to inject demagnetizing current. Here you can see all have negative part. So here you can say that means how we are implementing. So this is based on the same constant parameter based, where we have instead of taking those 3 variables data from experimentation, we will just take only one variable, and which can be easily calculated by this IDM minus using this formula 2.93. You see, means during experimentation, means if we are getting maximum torque at minimum starter current, so in that case we have to just note it down this DXS current, QXS current, and we are usually can get this IB. Okay, but if you want to go for lambda M, LD and LQ, so that will take a lot of time. Okay, so just by IB, we can easily implement our MTPA algorithm. Okay, so if it is constant, then with one just iteration we will get my MTPA algorithm working. But if it is varying, if IB is varying, so we need to have multiple points. So multiple points will eventually take your memory. So if you have less memory, if you have concern for your memory, then we can go for at different load, means by linear interpolation, means by taking at 1/4 of load, rated load, 50% load, 75% load, 100% load, we can easily realize using linear interpolation without much computational effort. So this is the equation. I mean, say by taking only just 5 points, we can remove that 0 part. So that is the no load value. So for breakaway points, we can easily get our MTPA method working. So this is all based on experimentation. So with the introduction of IV, so much efforts can be reduced to calculate your MTPA optimal point. So there is another way we can estimate this IV using algorithm. So as you can see that the cross coupling part is already there in the IPMSM, and we are using those estimated value for our controller algorithm. So here we have put this no load value here, lambda m, LD, and LQ star. These star are means these are taken at no load value. So if you means calculate this from the algorithm, means linearized equations, means how we remove this cross coupling terms using decoupling, you can see we will get this 2.98, where the variation in the quadrature axis inductance can be found using this equation. Okay, and also lambda m can be, means a change in the flux linkage can be found using this equation. But here you can see that the lambda m and del LD are dependent here. This two rank matrix, so we are not able to get these three variables at exactly same time. So as I told that d-axis inductance have higher reluctance path, so there is a very less chance of variation. So if there is mild saturation in the d-axis path, so we can neglect the variation of the d-axis inductance. So in that case, it will become more easy to estimate those parameters, the change in the estimate parameters. So if I'll put those equation in this conventional equation, our current angle, we are able to get our optimal current point. Okay. So as you can see that the same trigonometric part is still remain, and also the square root term is there. So it will be very, it is not means wise to implement this in a low power microcontroller, so that will consume a additional microsecond, 2-3 microsecond it will take to execute. So that's why I will go for this space current based calculation, and by solving this two equation, we are able to get able to get this last equation. You can say this base current can be calculated easily using q-axis voltage, q-axis current, d-axis voltage, and d-axis current, and also because there is no variation in the d-axis inductance, because we are assuming, because there is mild saturation, and this is generally for low to medium power machines, so we can assume that the d-axis inductance is maintained constant there, because there is no variation. We are going to see that if there is any effect of this d-axis variation on this base current. Okay, so also there is another term here, RS. So RS is also going to change. So, but in generally in IPMSM, there is a 5% variation in all kind of machines. So at full load, there is only 5% variation on the starter resistance. 5% is not going to affect that much. Okay, as the voltage are very high, means in terms of 100 volt, and the voltage drops, the D and q-axis voltage drops, starter voltage drops are very low, so it does not affect the estimation of this current. Okay, so as you can see, means the effects of the IV, means base current with parameter variation are also shown. So as you can see, with variation of primary magnetic flux linkage, there is no variation of base current. You can see that there is no variation. Okay, and also with LQ also there is no variation, but here you can see that with RS, means with the starter resistance, there is a variation, but there is very minimal. You can see that I have changed it to 50% increase in the starter resistance, but still I have not seen any significant variation here. But with the d-axis inductance, there is a high variation of IIB. So it is difficult to implement in IPMSM, which have large variation in the d-axis inductance. So, okay. So here you can see that how we are estimating the base current using the state variables omega, IQ, ID, UV, EQ. So using that equation, just with IN, with our new control variable IN star and this base current, estimated base current, we are able to implement MTPA algorithm. So this does not require any experimental procedure or anything, just this loop will work for online MTPA. Okay. So this is the figure 2.3 for source, the entire control structure here. The decoupling terms are there, the estimation of the base current is also there. So from that ID star, IQ star are estimated. And other thing I have already explained. Okay. So now we're going for the hardware realization of this algorithm. Okay. So this is a launch Excel 28379D. You already have seen this. This is one means this is the lowest, means a low cost microcontroller, lowest one I can say. So for that I developed this board here. Means there are 24 analog signal you can take with a 12 bit. Okay, so I have taken only just a 10 ADC. ADC, and for that signal conditioning circuits are built here, and there are means 12 PWM pins I have taken out from this one, and 2 enable signals are also required to control your PWM. If there is any kind of emergency occurred, we can emergency means if there is any kind of faults, because we are sampling those currents based on 3-phase current, so there must be a control part is required to turn on turn off this algorithm. Means during fault condition, if there is a overcurrent fault, so we can easily do that from this microcontroller side. Well, softwarely, not hardware, but we can easily enable disable this PWM signals. Okay. So this is the signal conditioning circuit I have developed using only one op-amp. Because I have chosen one op-amp means automatically if you will use more than one op-amp, it will add noise to your digital output. Okay, so here the digital range is actually 0 to 4095, so that will correspond to 0 to 3 volt. So that's why we have implemented using a OP2350 op-amp from Texas Instrument, and there is a ADC register is also, means there is a there is a current limiting register is also there in 100 ohm. There is a 2 nanofarad resistor, a capacitor, ceramic capacitor is also there. So you have to place this 2 nanofarad capacitor as much as close possible to your ADC pin, so that it will eliminate your noise. Okay, so from that I have checked with a signal generator. You can see that it is adding a 1.5 volt offset to your input signal, whether it is a sinusoidal signal or triangular signal. So this is also based on based on your op-amp specification also. So you have to choose a op-amp of high bandwidth. Okay, so low bandwidth noise will introduce automatically to your digital output. Okay, so in that case, it is difficult for you. Means you see there is only a half LSB variation here. Means your mean value is 2088, but there is only half LSB. because only the last part of the LSB is only vary. Okay, so if you go for other kind of UPAM which have low bandwidth, you can see there is a 10, 20, 50 digital count variation there also. So and okay, so also your PCB design is also means you have to make it really good. Means there are a lot of design criteria are also there. Means with that we have to follow those to reduce this noise problem. So the offset means we have intentionally add this offset because we cannot sample negative voltage in our ADC pin. Okay, so this offset can be removed using in software. So you see, means I have removed this one of the offset. This is not for here, not for this figure. By putting 210G means I have to get this value means at 0 current. So when no current is flowing, there will be no voltage at the input side. So I can easily get this value, digital value, using either debugger or with MATLAB simulation. So from that you have to get this offset, and using software you have to remove this offset. Okay, so and in case you have to calculate the gain. Okay, so you have to get the real-time value, means real world value of your current. So you have to get reconstruct your current here, because it is already changed to a volt, because we have gain here in this current sensor part or voltage sensor part. We have already gain introduced. So instead of calculating individual gains, you can just give 2 ampere current, and you can check how much voltage I am getting at this output, and just using this gain I can easily get my real current. Okay, how much current is flowing to the starter winding. Okay, so these are the 2 voltage and current sensor which are available in the market. You can easily get from Delhi-based VP Electronics. So they have introduced an additional OPAM here, that is a negative gain OPAM. So because of that, your means this is introduced because to increase the gain. Okay, so by using a simple trim pot here, we can increase the gain of this OPAM. So you have to introduce means another minus to your gain. Okay, so when for positive voltage it will show you a -1, for negative it will give you positive. So you have to introduce a -1 to your voltage or current gain, means in software, not in hardware, because in hardware if you want to do, you have to add another negative amplifier. Okay, so this is based on a Hall-based voltage sensor and a Hall-based current sensor. Okay, so but also there is a benefit of this kind of structure also. By additional OPAM, we do not have to add multiple winding, okay, in the current sensor, but and also you can go for very low voltage also. So in that case, you can make high gain here. It means without sacrificing your resolution, you are able to get good accuracy in measurement. Okay, so as I told, means in this C2000 there are only 2 DC ports are available. Okay, so means if you want to take 4 results, means generally 4 results are given in the publication, or means if you want to see more data, means what are the data actually, what are the state variables you want to plot or anything. So we have only 2 DAC ports are available. So in that case, what you can do is that you can easily build this PWM based DAC. So here you can have a low pass filter, means a combination of a resistor and a capacitor, means you can easily make a low pass filter. And by giving it to a PWM channel, you can easily recreate your input signal. So some of the means results here, means the performance of a inbuilt DAC and PWM based DAC. So you can see that this green one is our PWM based DAC. So there is a little lag here. So it will automatically you will get, means when you have a low pass filter. So there is a phase delay here, but it able to generate this your input signal. Okay, so this one is taken at 50 Hertz. So there is a little delay, but as you can see, if I will increase this means if I'll increase the frequency to 10 times, you can see that the DAC is not able to change. Means why it is looking like step, because I have given one sample time here. Means here the sample time is 200 microseconds. So for 200 microseconds it will be constant. Okay, it will be constant. So here that's why you are getting this step variation in the DAC output, but there is no variation in the no step kind variation in the PWM based DAC, but there is a significant phase delay you can see here. So that is the problem with the PWM based DAC. So you can easily get 12 outputs, 12 analog outputs from 12 pin. Okay, so you can simultaneously can see those variables how it behaves. Okay, so now I will go for this PWM part where there are means two optocoupler I have used to isolate your high voltage circuit to your low power circuit here. So I have used this kind of configuration where you can prevent shoot through. Means there is a tendency, means of simultaneously giving the same PWM signal to upper and lower IGBT, which will create a shoot through. Means if you have your inbuilt design, means inbuilt inverter, means you are designing yourself without any shoot through protection. So in with this configuration, it can be avoided. Means if when you are giving one to the upper IGBT, means it is not possible to give one to the lower one. Okay, so this is how, means our auto isolation circuit were built using, means for using 67137 for our inverter. Okay, so now we'll go for this calibration. So we required absolute position for our motor drives, motor control algorithm. So we have to implement, and so we have to calibrate our position sensor so that we can get absolute position of our rotor. So this can be done by either zero torque calibration method or back EMF comparison method. So in that case, you have to rotate your rotor, means manually or by prime mover, and you have to means you have to synchronize the zero crossing of your angle, your rotor angle, which we are getting from encoder, and also with your back EMF. Here you can see that the back EMF zero crossing and means zero of your rotor angle is synchronized here. So by doing this, you can this is the actual, means your absolute rotor angle. Okay, after calibration. So I did not show you before calibration. It will be anywhere. Okay, your zero crossing and zero crossing of your rotor will be anywhere, but like this. Means this is actually taken from VAB. Okay, line to line voltage. This is all after calibration, but you will get like this. Okay, So after calibration, you have to make both the zero crossing synchronized. Okay, and you can see the shape of this EMF. So it is not looking sinusoidal. There are high order harmonics are there. So this one is actually so this is not an optimal design. So you will find the pure sinusoidal waveform also from high-end IPMSM, but here you can see because of the slot harmonics, some harmonics are introduced here. Okay, so this one is taken from line-to-line voltage with your rotor angle. So there is no way you can calibrate with your rotor angle using line-to-line voltage. Okay, so you have to access your neutral point of your machine. Okay, so that's why I have given. So somewhere in some cases neutral points are not given from IPMSM. So there is no way. Okay, so this is the MATLAB implementation, how to get your rotor angle from EQP block here. Means it is already there in your MATLAB Simulink library. So we required these register value, and also index point is also required because this is a absolute, means our rotor angle should be absolute kind. Okay, so so we require index point also, and also you can see that means your encoder have only one index point, so it will give you only one, means mechanical angle, means it is in between 0 to 360 degrees. So to do that means we have 4 pole. This is a 4 pole structure, so we have to multiply with 2 here to get our electrical angle. So by this mode calculation, I can easily get a sawtooth signal like this. Okay, if I will not add this, so the angle will be continuous. So I will not be able to get zero crossing. Okay, so here you can see that because of means with incremental encoder, it is not possible to estimate speed below some base speed or below some speed. So we have to implement other algorithm there also. So so we have to implement another kind of speed estimation technique. Okay, so and also with the position we can easily calculate the speed also. So by introducing a delay to your position, and in between them, means if you know this delay, means these delay are all simple delay, means you have to mention how many delay you have to introduce here. Means the D is defined, and because according to this D, we have to calculate this speed gain. Okay, so the difference between this speed count at a different sampling point, we can easily get this speed. Okay. Okay, so this is the simulation of the control algorithm. So I have implemented this algorithm below base speed and above base speed. So as you can see that it will operate only at MTPA with only MTPA algorithm. So during the acceleration, and say this one is running at no load. Okay, so during acceleration you see positive current here, and during deceleration you can see negative current. So according to the current means according to the requirement of the speeds, automatically the speed loop will automatically decide this current. Okay, whether it will be positive or negative. Okay, so as we are trying to implement MTPA, you can see there is a demagnetizing current also. Demagnetizing current, and you can see that it is not violating the maximum voltage limit limit. Okay, so here I have chosen 150 volt as the maximum voltage. So during dynamic condition also it is not exceeding this 150. As the load is not applied, you can say that the maximum voltage is not 150. Okay, so if I will apply a load, so automatically it will be situated to 150. Okay, so we have to set some margin for your load term. Okay. So now you can say that if I will need to operate at above base speed, so with MTPA we have to inject more current into the D axis. There is no increase, and there is no injection of in the Q axis current, only just D axis current. It is putting more current in the D axis, demagnetizing current, and as you can see, as D axis current is increasing, means negatively, means you see the Q axis current is also reduced. Okay, and you can see that means the maximum voltage limit is violated here because that additional loop, that voltage loop is actually calculating this extra current, means which is required for demagnetization. Okay, so here you see, means the voltage is limited to 150. So we are not able to apply more voltage to IPMSM due to the DC-link voltage, due to the limitation in the DC-link voltage. So this cycle is continued, and you can say there are 4 cycles I have shown here. Okay, so this is now means as you can see, the variation of DQ axis current before this method and after this method, means due to the parameter variation, you can say there is a significant variation of actual DQ axis current and our required D axis current. As you can see here, the ISC is maintained, means this is the first one. Before switching to our estimated method, it is around 8.51, but after it is just 8.41. So this is all based simulation results here, and you can see after activating the base current mechanism, you can see the DQ axis is actually tracking the actual required current, I mean actual MTPA trajectory. So this is happened for all method here, but in except method 3, where you can see that after activation also there is slight variation in the actual current and the required current. Okay, so this is done only for the variation of the flux linkage and the quadrature resistance inductance. But when I we also try to look whether there is any variation with D axis inductance also. So in that case, the parameter of base current is actually not accurate. So in this 3 result, you can see that after 20% variation of D axis inductance also, there is a little variation. So it is working fine with up to 20% variation of LD. So those motors which have this specific variation, so up to the means in that case we can apply this algorithm. If there is more variation of LD, so we cannot apply. So that is the disadvantages of this algorithm. And also before implementation, after implementation, you can say that you can means the actual base current and nominal base current, and you can say that before this self correction of base current is applied, and after it automatically the operating point are shifted to this actual MTPA trajectory. That's how it is jumping from one trajectory to actual MTPA trajectory. It is shown in this figure 2.50. Also, you can see that there is no variation of estimation of base current with load torque also. So it can be applied with in dynamic situation also, not in just a steady state. Okay. So these are some of the screenshots I've taken from that model actually. So I'm unable to show you everything inside of this. Okay. This is the, in some special session I will give more details actually. So here this interrupt will generate this inner current control loop. Okay, so there are retransition are required if you want to communicate between subsystem which have different sampling rate. Okay, so all this subsystem have a different sampling rate. That's why, and also this is a interrupt based. Okay, so interrupt based. So we are actually sampling those voltage and currents at specific point of your carrier signal. So this should be taken as a high priority. Okay, so these interrupt based. So according to that, we have to mention this interrupt here. We cannot just operate it in this. Not it should not be softwarely triggered. Okay, so in that case, you will get error which cannot be easily solved. Okay, so with this interrupt, sampling time is 200 microsecond, which is decided by the switching frequency. So here I have taken 500 sorry 5 kilohertz. So according to that, the sampling is chosen, and here in this how the current are sampled, it you can say means how I removed the offset, means which are added to the signal conditioning circuit, and how I actually got those variables, means our real world variables here, real current, using this gain. Okay, so these are all based on experimental analysis. Okay. So, and this is your DC-link voltage, because you have variation in the DC-link voltage due to insufficient means if you are actually getting DC voltage from a three-phase source, there will be automatically a ripple 6 times of your frequency. So that need to be removed. Either you can remove it with filters or just in software you can add a moving average or any kind of first order filter also you can implement. Okay, according to that you can get your DC-link voltage in software. Okay, so there are multiple sequence are available, because you have to implement it using in only closed loop manner. It cannot be operated in open loop, because in open loop you will get vibration. Okay, so so when index from that encoder is found, then only it can be able to work. This algorithm will work. So like that, I have designed it like this way. So I have external control pin here, which will start my means speed control loop and current control loop at same time. So if there is a lag between this, then it will create problem, because this is a dynamic system, not a static system. So automatically you will see a jerking, or there will be high current in your motor. So after getting the absolute position of that rotor, then after that we can implement this algorithm. Okay, so from this IDIQ reference, means this is the MTPA algorithm, which is just a constant parameter based algorithm here. And the reference is generated from this speed loop. It is given to this current control loop here, and after that it will generate this V alpha and V beta using Clark and Clark transformation. And before that, means when closed loop is not enabled, it will automatically, means this V alpha V beta will give 0 voltage. There will be no voltage will apply to you to the motor. Okay, so after closed loop enable, it automatically gives the required amount of voltage voltage which is required for IPMSM for specific operating point. So this is the executive algorithm which is it's implemented using a MATLAB function block. So according to that, we have to calculate the modulation means signal, and also you have to check that all these signaling blocks are actually are taking on interrupt means sorry, unsigned integer, means 16-bit unsigned integer. So you have to change it to unsigned integer before using this block, and also these are also giving unsigned integer. So you have to convert it either to the floating variable. Okay, so a single data type is actually recommended. So you have to take that one into consideration. Okay. So this is the hardware prototype that I have developed in NIT Rourkela. So here 3 voltage is given using a variac here, and using voltage sensor, current sensor, and there is another PMSG is connected to give load torque to our target IPMSM. And that TI lab is used to for controller means control algorithm implementation using opto isolation and voltage shifter board. The drivers are same Stepper 32 Pro. So this is the rating of my motors, and its parameter means no load parameter, quadrature axis, D axis inductance, resistance, inertia, that is the combined inertia of both and motor and generator. Okay. So before that, we took our closed loop current analysis, means whether it is tracking properly or not. So that is the first thing we have to take from here. Means you can see that means one current loop at a time. So this is the first step we have to take. Means when we are designing multiple loop control systems, so we have to go means we have to start from the inner current loop. Okay. So as you can see that when I am giving this 1 minus 1 minus 1, so there is no variation in the speed. Okay, and also it is able to track properly as it. Okay, so when I am trying to give the same signal to this quadrature axis current, you can see that it is rotating in positive direction, negative direction. This is because your IQ is equivalent to your torque. So whatever you will put IQ, it will automatically generate some kind of torque. Either you can block it using some kind of obstacle. Means if you are not able to stop your rotor, means with any external device. So in that case, there will be movement. Okay. So why I am giving only positive negative is because the average torque will be 0. So in that case, if you try to block it with something else, maybe it will break that thing also. Okay. For high power machines, means that is for high power. So it is that's why for making this total torque total average torque 0, I have given this plus or minus 1 like signals. Okay, so you can see that there is movement, there is also rotor movement here. Okay, so it will take 2 positive cycles, then after that 2 negative cycles. Means positive cycles means it will go to one direction where you can see there is increase in the rotor angle, then after that it's sudden there is decreasing in the rotor angle. Okay, so like that it will perform, but you will get your required current loop working. Okay, so now you can say those implementation where you are during this acceleration, you can say the IQ is positive, and IQ is actually tracking your actual quadrature axis current is tracking with your reference, and your movement of your rotor is also shown here. From 0 to 360 means you cannot get 0 to 360, you will get 0 to 3 volt from your DSP. So this is also shown here, and in here the means during the acceleration you can see that there is a high current in rush, you can see that, and that is actually limited by your current limiter. So you have to put limiter means to prevent means high current to your inverter. So your current is limited with that limiter. Okay, so like that you can see from the 3-phase current also. In the DQ axis current also you can see that, and for MTPA implementation, D current is also applied to your motor. Okay, this is your 3-phase current. The variation of 3-phase current with the load also is shown here. 3-phase current with at no load means here you can see that the slot harmonics have an effect on the current. So and also from the DC means when the rotor is at steady, you will expect a zero frequency there. Means the current will be DC there. This is not the case with the induction motor, where the current will always be AC. Okay, so as I means remove that load, automatically the motor will start rotating out. And here you can see that when the current is means your torque, when you apply your torque, automatically you can see your torque is sorry, your speed is reducing. So by means that is the disturbance is not means effectively means your speed regulator is not effectively remove the disturbance. So by proper tuning you can easily remove this. Okay, so from in figure 2.60J you can say that by applying low torque the disturbance is removed a very less time. And you can see that from another point of view here in this 2.60L means with the low torque I am trying to operate my motor at both positive and negative direction. So this is the moment and the rotor angle here, and also these are some of the results for specifically for the MTPA algorithm. So after activation of self correction method, the starter current is reducing, as you can see from here, and it has been also compared with other conventional method, that is virtual signal injection method. Also, you can see the variation of DQ axis current with the starter current, where you can see that the magnitude, the peak of your starter current is also reduced when we try to implement MTPA. Okay, so which will eventually reduce our copper loss. And also with the constant parameter based variation is also shown here, means with constant power means the difference between constant parameter based method and self correction based method. There is a slight decrease in the starter current, but the method is effective compared to the constant parameter based method. And how it behaves means that your IB is dependent on the parameter. So according to the operating point, changes in the operating point, you can see that there is a variation in the base current also. You can see that it is estimating your base current. Okay, so this is these results are taken just to there is no need of this THD all harmonics. These are just a part of the formality. Okay, so here the THD means from the THD of the current you can find high frequency means switching frequency component or twice of the switching frequency component in your starter current. And also with the variation of the load, you can see that at low torque you will find high means low order harmonics here in this region. Okay, so based on the analysis we found that with 3 different method is comparatively same with this method described in this described in reference 11. Okay, so that what we have. We are taking as a benchmark to benchmark our method here. So we have found that our method is comparatively better than this method, virtual signal method, but not better than this one. But that is a traditional method, LUT based method, which consumes a lot of experimentation time. Okay, so that's what we have taken for benchmarking. Yeah, and you can see the reduction in the copper losses compared to this virtual signal injection method. With the method 1 and 2, it is effectively reducing the copper loss, but not that much able to. Your method 3 is not able to reduce that much. Okay, so also we have analyzed the code execution time also. So we have effectively reduced the code execution time with method 1, 2, and 3 compared to other method. This LUT based method is consuming very less time because there is no calculation is there or estimation any method is there. That's why. But other methods are consuming a lot of computational resources. So we comparison purpose we have given this code execution time. Also dynamic response is also given here because LUT based methods are working comparatively better than other methods, means all methods. So we have given a dynamic response time of our method also. Here in figure 2.68, you can see that MTPA proposed MTPA trajectory is closely resembles, closely tracking the actual MTPA trajectory and compared to other method. And here you can see that the LUT based method is same as actual MTPA trajectory. Okay, but with limited operating point, the variation may means the operating points may differ. Okay, so this is the performance evaluation chart where you can see that the proposed method is means there is very less implementation complexity in this method compared to other method, where LUT based method is complexity is very high due to the high requirement of experimental times, dedicated hardware, and also efficiency is, but with those method efficiency is high, but we are comparatively reaching to that point also. And you can see method 12 is not able to give high efficiency despite its high code execution time. And also we are able to achieve high dynamic response with our 3 method compared to your lookup table based method. So these are some conclusion just I have written to give a brief about what we have done so far. So these are the references. If you have any interest on this IPMSM drives, adjustable drives, or EV or industry application, you can go for. Okay, so this is all about this workshop, and if you have any doubt, any kind of queries on anything, especially motor drives, so you can ask me. I have already taken a lot of time actually. Right. Hello.
Hello, Joy. Hello, Manoj.
Anybody has any query? Yes, sir. Yes, sir.
Yes. Very good presentation. Nice presentation. Okay, so I'm requesting our participants. So
Thank you.
if you are having any query, doubts, please let us know.
Hello.
Yes. Yes, you can ask.
Sir, good evening, sir. Sir, thank you so much for sir wonderful presentation, sir.
Good evening.
Sir, actually, I want to
Thank
work in this area, sir. Actually, for control of induction machine or synchronous motors. But currently, sir, I am very basic level, sir.
Okay.
Actually, I am learning about the DTC and FOC. So, sir, I want to know, sir, do I
Okay.
need to means thoroughly understand this DQ transformation, ABC transformation for switching for the maximum power per ampere methods, or sir, can I contact you for means if I means learn these algorithms for the control of synchronous machines?
Yeah.
Actually, I'm very interested, sir, in this area.
Yes, you can reach to. Okay,
So,
you can reach to me. That is not a obstacle there. So you need to go for machine analysis. Okay, so that is a course you should go for. So from that you you require a depth analysis of this DQ level analysis. Okay, so these are all simplified version. Okay, so first go for machine analysis subject means in that. And so there is a book. I don't remember that book name. Okay, first
you
go
can
to
share
that one. And I can share. I don't remember the book name. You can ask Arnab sir. Means he can tell. Okay,
Kraus
so that
is
is
there
a
one
subject.
Kraus.
Means we. Kraus. That is Kraus book, but full name I don't remember.
Sir, Kraus means CROUSE.
So,
Sir,
K,
Kraus.
K. It will start from K.
K.
It will start from
K.
It's, I think John
KRAUSS.
Cross. John D. Cross. KRAUSS. I'm Prakash from Bharat Institute.
Yeah. That
KRAUSS. I think so, sir.
that book will help you.
Yeah.
Oh, sir, can I
Maybe you will
contact?
get. I don't know you. Yes, you can contact you. You will get
Sir, via
my
email or
mail address.
so can I share? Can you share, please, your
By
email?
mail. Yes. My mail is Jena JENA3471 @gmail.com.
Sir, please,
JENA3471.
Sir, GEENA.
Hello. No, JENA.
I will share. Don't worry. Okay, you
Yes,
WhatsApp me. I'll share his.
Sir will share. Okay.
I'll share his mail ID. Don't worry. You
yes,
WhatsApp me.
thank
I'll share
Okay.
Manoj's
Thank
mail ID. Okay.
Thank you so much. Thank you so much, sir.
Thank you. Any more comments? Any more queries? Okay, so I'm not
You
able
can
I
to
have
ask
a
see.
for all kind of motors.
sorry.
Okay.
Yeah,
Sir,
sorry.
my name is Prakash from Bharat Institute of Higher Education Research, Chennai.
Your voice is not audible. Okay.
My name is Prakash from Bharat Institute of Higher Education. Sir,
Actually, your voice is breaking.
Your voice is not audible, sir.
Oh, fine, sir. Then I'll put in chat box.
Now, yeah. You can. Sometimes it is coming, sometimes it not.
Yes.
Hello. Sir, can you hear
Yes,
me
sir.
right now?
Yes.
Sir,
Yes,
my name is
I
Prakash,
can hear.
Bharat Institute. Sir, is there any demo simulation available in MATLAB? Your ideas? Or any
Demo
idea?
simulation are, I think, available for latest.
Okay.
For latest MATLAB, I think demos are available. Means I think you will get a lot of reference. Latest you have to go for latest MATLAB 2024-23. I think now they are giving those implementation and other, but those will be based on only specific data types, fixed data types. So these hardware implementation generally requires fixed data types variable. So we have done with only floating data types. Okay.
Okay, sir. Okay, sir.
So
Then
you
we
will
will
get a lot of reference. Okay.
we'll
You
try,
just need
sir.
to search.
Okay, okay, sir.
Yeah,
Thank
you
you.
will get. Okay. Thank you. Anybody else?
I think no one is there. Thank you, Manoj, for your very beautiful presentation. Okay, so it's really nice. I have seen the entire
Thank you, sir. Thank
slides.
you for giving me this opportunity.
Okay, it's really very good. Okay, as well as very again, thank you for your giving your valuable time. As you are a very busy in weekend, you are giving us some time and share your idea to the participants. It's a very good. Okay, so I hope participants also getting some idea, as well as I hope they can also carry on their work in this domain if they are interested. Thank you, Manoj. Okay, again we will meet.
Thank you.
Bye.
Thank you. Thank you. Thank you very much. Thank you, everyone. Thank you.
Thanks, sir. Sir, thank you.
Thank you. Thank you.